In the previous couple of lessons, you learned about the other two types of particle radiation. First, you learned about alpha particle radiation. Big particles made of 2 protons and 2 neutrons that don't penetrate matter very far because not only are they enormous as far as radioactivity goes, they also have a really high charge, 2+. Next, you learned about beta particles, made up of a single energetic electron flying very quickly with its 1 negative charge and its very small mass. You learned that beta radiation was able to penetrate a lot farther than alpha radiation because its charge wasn't so great and its mass wasn't so great. Now you're going to learn about the third type, the most penetrating type of particle radiation, neutron radiation. Again, we're going to start by looking at the properties of neutron radiation, followed by the range of neutron radiation, how far it goes. We'll look at what's required to shield against neutron radiation, and we'll look at the type of hazard that neutron radiation is. So to begin, let's consider what neutron radiation is. It's actually very simple. It's made up of a single neutron speeding away from wherever the radioactive source is. Neutrons are neutrally charged. They don't have any charge at all. And they have the same mass as a proton, 1 atomic mass unit. Because neutron radiation has no charge and there's no electric forces acting between it and other atoms around it, neutron radiation is the most penetrating type of particle radiation. In fact, some sources say that its range is not really even predictable. Other sources estimate that the range in air of neutron particle radiation is several hundred feet, maybe even up to 1,000 feet or more through the air. This makes neutron radiation pretty dangerous. Not only is it ionizing radiation that can break down things like the molecules that hold together your DNA, but it travels extremely far and it's very, very difficult to stop. To shield people against neutron radiation usually requires a shield that has multiple layers or is specifically designed for the type of neutron, because there are 2 types of neutron radiation. There's fast neutron radiation that has a whole lot of energy, and there's slow neutron radiation that doesn't have as much. To guard against slow neutron radiation, some simple substances work as a shield, like water or plastic. Fast neutrons, however, are the really dangerous ones, and those can only be stopped by thick layers of steel, concrete, and lead. What happens is the neutron enters the material, and as it flies through the steel, concrete, or lead, it collides with the nuclei of the atoms in those materials, and when it collides with those nuclei, it loses its energy little bit by little bit until eventually it's stopped. To shield against all neutron radiation requires a multi-layered shield for fast and slow neutrons. And then finally, considering what kind of a hazard neutron radiation is, it is definitely an external radiation hazard because it easily penetrates any matter. It can penetrate the human body very easily from the outside. As those neutrons travel through the human body, they can collide with and destroy the atoms that make up the DNA in human tissues. Exactly how does that happen? Well, let's take a look at how neutron radiation is ionizing radiation. These are the typical carbon atoms that are found in your DNA in molecules. Notice that they're bonded together still. Again, these are not exactly what your DNA would look like, but they're an approximation of like what a part of your DNA would look like. And this is a neutron radiation particle that is going to bombard your DNA. And what ends up happening is neutron radiation will stick to the nucleus of an atom, changing the chemistry of the nucleus so that it's no longer stable. This is no longer a stable carbon atom like it was just a moment ago. So this nucleus has to radioactively decay to become stable. Now, there's a lot of different ways that radioactive decay can happen. In this case, one of the neutrons is going to change into a proton and an electron, and that will make the nucleus stable again. Now watch what happens as that occurs. When the neutron changes to a proton, it changes the type of atom altogether. Now, instead of having a carbon atom, we have a nitrogen atom, instead of having 6 protons, it has 7 protons. Because it has 7 protons, it also needs to have 7 electrons. So it's just going to hang on to those extra electrons that it had when it was bonded with the carbon. And the carbon is no longer going to bond to the nitrogen. It just chemically does not work that way. Also, look at what's left over. Do you notice that in addition to everything that just happened because of the neutron radiation, there's now a beta particle just waiting to ionize yet another atom somewhere nearby. So not only does neutron radiation cause the breakdown of one specific atom, but it can also cause breakdowns of other atoms as well. Now, did you notice the mechanism by which neutron radiation worked here? It ionized atoms by making another atom radioactive. And that's what neutron radiation is able to do that no other type of radiation is able to do. Neutron radiation can change one type of atom to an entirely different type of atom by causing it to become unstable and to decay. Now you understand a little bit more about neutron radiation. Made up of a single neutron, no charge, 1 AMU mass, very difficult to shield against and stop because it has such a long range, so you have to use different layers that contain concrete or steel or lead in one layer and plastic or water in the other layer. It is definitely external radiation because it goes right through your body, so it can harm you as it travels through. And it causes atoms to ionize by making them unstable and then causing them to decay radioactively.